Hi everyone, we are from Group 1. Okay, I'm the first presenter. My name is Hani. With me is Muzaffar, Suraya, Mujahid, Akil, Dalila, and Rosie. Next. So first we will discuss about the introduction, about the background of our study. Next. The journal that we are use is Simplifying Tree-Based Method for Retail Sales Forecasting with Explanatory Variables. We get the journal from the Operational Research Journal from the Elsevier publisher. Okay. The journal objective is to improve forecast accuracy by integrating explanatory variable, for example, promotions and holiday into tree-based models. The approach used in the journal is gradient boosted regression tree, and it was benchmarked against random forest and traditional statistics method to prove the efficiency. The result is the study proved that tree-based method offer better in terms of model accuracy over the traditional time series method. Next. Okay. The contribution in the journal is the paper demonstrates implementation of the tree-based machine learning method that can outperform the traditional forecast method without doing any complex architecture. So, the paper makes a methodological and practical application to the field of the retail forecast. While the gap in the study is the machine learning models are too complex, expensive in terms of computation, and difficult to implement compared to the traditional forecast method. Therefore, the authors develop and validate a simplified tree-based machine learning approach using light GBM. The model helps to remove complex features in the data. So, from the study, it proved that simplified machine learning method can outperform the traditional method by 11% accuracy. Next. Okay, methodology. This journal used gradient boosted decision tree, for example, like GBM and XGBoost. The concept is we train a single model across many time series, for example, product and store simultaneously. So the model are able to learn the cross series patterns instead of learning the data individually. The paper also demonstrates the use of feature engineering instead of learning. The paper demonstrates the use of feature engineering on the explanatory variables, for example, price, promotion, and marketing events, as well as the lag features. Okay, the model is better compared to SES and ARIMA. Performance is assessed in terms of the efficiency. They're using metric, for example, RMSE and WRMSSE. In addition of the forecast, the study evaluates operational value through inventory policy simulation that shows streamlined machine learning model can lower the inventory cost or raise service standards without requiring the intricacy of the black box models. That's it from me. So I pass to the next.
So here are some findings from the journals. The first one is on the forecast accuracy. So the study shows that simple tree-based methods, particularly like GBM, improve forecast accuracy by about 11.5% RMSE compared to other traditional methods like exponential smoothing and moving average. It was tested over the period of 3 months with a forecast horizon of 7 days. And this improvement was consistent across multiple data sets, including a Belgian retailer's data, which consists about 4,000 products, and M5 Walmart competition data set. Okay, and the next finding, we found that the Shapley value analysis confirmed that the explanatory variables significantly boosted both accuracy and interpretability, incorporating like promotions, events, and external drivers. And other than that, the simplified light GBM framework was computationally efficient and scalable to large dataset. It required only basic feature engineering and off-the-shelf software. Hence, it is easier for retailers to adopt without heavy infrastructure and advanced machine learning expertise. The training time and resource usage were minimized while accuracy remained high. And last but not least, beyond the accuracy, the study demonstrated tangible business benefits through inventory simulations, like higher service levels, lower inventory costs, and reduced volume effect, meaning fewer fluctuations in orders and inventory. So these operational improvements highlight how better forecasting translates directly into improved supply chain performance. Then I will pass to the next presenter on the mic.
Thank you, Soraya. In this section, I will explain the analytical approach used in our selected journal and how it's applied in our study. Let's start with the forecasting family. The journal explained that many retailers still use traditional statistical models. This happen even though machine learning models often give better accuracy. One main reason is that many machine learning models are hard to apply in real business setting. The journals compare local models such as ARIMA with machine learning models like random forest. Random forest can be accurate, but is slow and use a lot of memory. Because of this, the journal support global tree-based forecasting model. In this approach, one model learns pattern from all products at the same time. Next slide. Now, let me explain what is Light GBM. Light GBM stands for Light Gradient Boosting Machine. It is a machine learning method based on decision tree. Light GBM builds many small trees one after another. Each new tree focuses on fixing the errors made by early trees. This learning process is called gradient boosting. We choose Light GBM for several important reasons. First is scalability. Light GBM can handle large dataset efficiently. It's run fast and does not use too many memory. This is important for real retail data with many products. Second, non-linear accuracy. Retail sales pattern are complex, is non-linear. Light GBM can capture this complex pattern very well. This helps improve forecasting accuracy. Third, simplicity. The journal shows that simple tree-based model already perform well. Light GBM gives strong result without heavy tuning. Light GBM also robustness and practicality. Light GBM is robust and stable across different datasets. It is performed well with minimal hyperparameter tuning. This makes it practical for real business use. Because of this reason, Light GBM fit both the journal's recommendation and our dataset. Next slide. Now, let's look at how Light GBM learns and how we design our futures. Can capture sudden change in sales. Next, our future selection follow our main group. First, categorical features. We use label encoding to convert stock code and country into numbers. This allow the model to recognize each product as a unique product DNA. Second, temporal features. We use multi-level leg 1, leg 2, and leg 3. These features help the model learn sales momentum over time. Third, economic features. We include price-related variables such as leg price 1. This helps model understand how price change affect sales volume. Finally, noise features. We remove non-transactional record like Amazon fee, cost, and bank charges. This filtering step improves data quality and model accuracy. Overall, these features design support the general conclusion that the explanatory variables and clean data are key driver of forecasting performance. Next. The Light GBM framework. The slide summarizes the Light GBM framework as a complete system. First, the global strategy. Light GBM use one global model or one super brand to learn from all products. This improves learning efficiency and scalability. Second, leaf-wise growth. The model expands the branch with the highest error. This improves learning efficiency without unnecessary complexity. Next, GOS and EFB. This technique reduces computation and memory use. They allow LightGBM to scale well to large retail dataset. LightGBM also works well with minimal tuning. This makes the framework practical and stable in real application. The framework supports diagnosis analysis. This improves transparency and trust in the model. Next. LightGBM model development. This is explained how the LightGBM model is developed from start to the end. We begin with the raw retail data. This data includes real sales record and some value may be missing. Next, LightGBM use gradient boosting. This means the model built tree step by step. Each new trees improve the accuracy of the previous one. LightGBM can handle missing data effectively. It does not require complex data imputation. This makes the model robust and when working the real data set. Finally, the result is a predictive model. This model is accurate, efficiency, and suitable for retail forecasting. Next. Enhancing model transparency and stability. We evaluate model integrity using residual analysis. Residual represent the difference between actual sales and predictive sales. First, we examine the histogram of residual. A balanced shape indicates that the model is not biased. Next, we use the autocorrelation function or SEF plot. This helps verify the seasonal pattern are properly captured by the model. We also monitor the average residual error over time. This allows us to check whether the model remains stable. Overall, these diagnostic tools help transform the model from a black box into the glass box. This increases trust and supports real-world decision-making. Next. Quantile regression for risk management. Finally, this slide focuses on the risk management. The journal explains that one forecast value is not enough. Manager also need to understand uncertainty. It's in our study we use quantile regression. This provide a range of possible future sales value. It helps manager plan for both low and high demand situation. We evaluate model performance using RMSSE. The journal show that better forecast improve service levels and reduce inventory problems. To conclude, the journal showed that simple tree-based model work well in retail forecasting. They perform better than traditional statistical model. That's all from me. Now I will pass to Dadila.
Now, moving into limitations and potential improvements, our analysis identified four key limitations highlighted by the researchers of the study. First, there's a limited exploration of long-term forecasting or short-term focus. The study primarily focuses on 7-day operational forecasts, but in retail, strategy is built on months and years, thus it neglects strategic long-term needs. Second, the study's dependency on data availability and quality. It relies heavily on perfect explanatory variables like promotions and events. In the real world, data is often dirty or missing, which could lead to a significant performance drop. So next, the study's framework relies on manual feature engineering. While this produces high accuracy, it requires a lot of domain expertise and time, making it difficult to deploy across thousands of diverse product categories quickly. And lastly, absence of external validation. The researcher highlights that validation of the study is limited to specific Belgian and M5 datasets, leaving performance in diverse global markets unverified. So what is the potential improvements? First recommendation is hierarchical integrations. As we commonly know, retail is not flat, it is built on products, stores, and regions. So by integrating hierarchical or multi-level modeling, it can improve accuracy and bridge the gap between operational and aggregate forecasting. The researcher also suggests to move the goalpost from accuracy to impact. It is to shift focus from purely statistical error metrics to real-world business impacts like revenue and customer satisfaction. And lastly, the current study model does not explicitly account for external shocks like global supply chain breaks or sudden shift in consumer behavior. So thus, researchers suggest exploring adaptive modeling strategies that can recalibrate in real time.
Moving on to the next part, business implications and theoretical contributions. For business implications, the first of all, is bridging simplicity and performance in forecasting. Basically, this paper contributes to forecasting theory by demonstrating that simplified versions of tree-based machine learning model can match or even outperform both traditional statistical methods and or more complex machine learning models, especially when explanatory variables are included. Second, role of explanatory variables. External drivers such as promotions or events are essential to unlock the predictive potential of relatively simple tree-based model. The use of sharp values to interpret variable importance also adds to the theoretical understanding of how and why certain predictors matter in forecasting models. The last one is scalability and practicality in forecast theory. Validating the approach on both large real-world retail dataset and the benchmark M5 dataset, which is real-world retail sales forecasting dataset. This paper provides evidence that scalable forecasting frameworks grounded in tree-based machine learning are theoretically applicable for various retail contexts. Next slide. Next. So for theoretical contributions, the first of all is improve operational performance. So the simplified tree-based forecasting framework from this paper leads to a better forecast accuracy compared to traditional statistical methods. This leads to higher full rates, lower inventory costs by avoiding overstocking, and reduce bullwhip effects in orders and inventory fluctuation. The next is greater practical adoption of machine learning methods. Traditional statistical forecasting remains dominant in retail because machine learning models are often too difficult to implement and maintain in practice. This simplified tree-based method reduces computational complexity while still retains its interpretability. Lastly is feature engineering with explanatory variables. Incorporating explanatory variables such as promotion and events was shown to be a major driver of improved forecasting performance. For retail businesses, this suggests that investing in rich auxiliary data sources and feature engineering, not just based on past sales history, can substantially enhance forecast quality and downstream planning decisions. Next slide.
So next we take this approach that was used in the case in the journal and apply it to our own case study. Passing over to Akhil.
Okay, for this slide, we are focusing on study comparison. The table highlights how the simplicity principle from a research paper was applied to a real-world business scenario. So the application of the LIGB light GBM model to the data online retail dataset successfully validated the simplicity principle outlined in the journal by listing complex flow transaction logs in the high impact features, specifically hard price and lags. The project proved that high performance forecasting does not require unnecessary complexity. This approach bridged the gap between the data science and management, providing a tool that that is not only computationally efficient, but also transparent enough for business leaders to trust in the decision-making process. So you can see that the model is like GBM for journal, for speed and accuracy, but for our practice to predict sales, data source M5 Walnut, and but we for this assignment using a data online retail UK Global goal simplicity simplify complex AI for managers, and for our practice predict sales with simple features, variable price event lags, and for our practice price lags. So we're going for the next slide. So for the data extraction, case study, extension, and objective, our goal is to extend the journal's simplicity principle to a global context using the data online retail dataset, scope, forecast monthly revenue, concurrently across 38 distinct global region. Methodology utilize a unified light GBM framework for speed, accuracy, and stability without complex assemble tuning. And for the number two, why use the data dataset? For global research, spends a full year 2011 of transactional data across diverse international markets. Granular variable provides key drivers including quantity, unit price, invoice date, and country for robust features engineering. Real-world validation of a complex high-volume environment to prove that simplified tree-based method can outperform traditional statistical models. So you go for the next slide for data exploration. So from raw data column name, we can see that data exploration show the first step in analyzing the data online retail data set. It display the raw data exactly as it looks before any cleaning or change are made. So for the top section, show a snippet of the actual data table. Each row represent an item sold in a transaction. For the data structure, the middle section tells us how big the data is. 541,909 observation. There are overall 500,000 rows of the data in this file. 8 variables, there are 8 columns of information for every row. So for the length unit, we have 38 countries. The store sells to customers in 38 different countries. And also 4,070 stock codes. There are over 4,000 unique products being sold. So going for the next slide. This is also a data exploration. For this one, to ensure our sales and reflect actual product demand, we implemented a rigorous cleaning protocol. We use pattern matching automation to flag all non-standard stock codes. However, recognizing that some valid products use unconventional labels like TCS boy, we add a layer of manual verification. This human in the loop approach allows us to filter out 14 types of administrative costs such as bank charges and postage while keeping unique product sales intact. The result is a highly clean dataset that prevent administrative noise from skewing our revenue KPI. So that's all for data explanation. So I pass to the next presenter for code explanation. Thank you.
To analyze the data, first we will install all the necessary packages needed. For example, OpenXLS, data table, tidyverse, lubricate, all of these. And after that, we call the library. So the OpenXLS is used for us to read the Excel file. After that, the data table is used for data manipulation, and tidyverse is the collection of packages, for example, ggplot and dplyr for the plotting and cleaning. Lubricate is for us to handle with the date. After that, like GBM, we call the package because we're going to apply the model like GBM. And Shiny for us to do the dashboard later. After that, scales is for us to make the numbers turn into a beautiful numeric number. And then the grid exchange. DT is the interactive data tables that we use in the dashboard later. Next. Okay, first, after that, we will load the data and then we'll convert the data to a data table. After that, we remove all the unnecessary stock code that can be biased to our model or code that is not necessary. After that, we will reformat the date into Excel format. And then we'll apply the monthly aggregation on the sales and the average selling price by month. Okay. Next. After we have load the data and clean the data, we will correct the data and check if there is any empty data or any missing in the data. So, since we noticed the data in 2011 is not full, so we need to scale the data. After that, we merge the stock code per country with time. And then we also fill in the sales quantity that is 0 or missing. After that, for the price, we use the price is still not available. We will, for that particular country, we will fill it with the price based on the global average. Next. Next.
I think this must, yeah. So I'll be presenting on the next section. It's on the next slide on feature engineering. So after cleaning up the data, we started off about 4,000 product stock code. But after removing the stock code, we have about 3,900 plus stock codes in total. So next we want to calculate the lags and also the rolling or moving average. It's all from the quantity variable. So we're trying to predict or forecast the quantity. Lag 1, 2, 3 is basically just the autoregressive portion of the model, and also we have the roll mean, which is the moving average, 3 months moving average which represent the moving average portion in Arimal. So it's pretty much similar. And we also pass in the price as a feature as well, so that it capture if there's any discount or reduction in price that may impact the sales of that stock code. Um, there is some missing data handling as well inside the feature engineering code, because we're using lag. So sometimes the price, for example, if it's a new product in that country, we don't have a price for that country, so we have to uh, impute using the average price from the global average price. So there is some missing data imputation as well in this session. Next, moving on to training the model. So it's basically we kind of concatenate all of the feature columns. Like 1, 2, 3 is all the autoregressive portion. The price and also the moving average is there as we calculated in the last slide. And then we also put in number of information here, month, which is the time, and then the stock code number and the country number as well. And then we define what is the target column, which is what we want to predict, which is the quantity. Um, we also then we tell that the stock code and the country number is a categorical feature. So we use this function lgb.dataset to to convert the data into a format that like GBM can read. And then under that also we define that stock code and country number is a categorical feature. So dtrain is the function that is the data set that the light GBM model can read lah. Then we define a function called train underscore quartile, and it basically is a function that accepts different alpha value, and this is how we define, as Rosie mentioned during her session, we needed the lower bound and upper bound. It's a little bit different from calculation from a standard confidence interval. We use the model 3 times, once for the lower bound, for median is the midpoint or the main values that we want to forecast, and then we also have upper model that we train. Then residual calculation also used in the Shiny analysis later is calculated over here as well based on the median model. So still talking about the function alpha, there's certain information that we provide in this training function. I won't talk about all of it, but for example, one of it is the alpha. We pass in the alpha into the model as a parameter. The number of leaves, Rosie mentioned about how many that we go leaf wise, and we pick, this model will pick the highest or the best fit leaves first. So that's why light GBM is faster, and that's hence the name light, because they want to grow the best leaves first. But we limit the number of leaves to 40 and inside this parameter. We already talked about this. Basically, we train the 3 models. Next, we go into forecasting. So basically, now we already have the model, and we want to use it to predict the future date. What we're doing is we have 1 year data, which is a full 2011 data, and we're trying to predict 2012 from the Tata data set. And the problem is, as we go from month to month, the difference that we introduce, or the extension that we introduce in this code, is we do it by recursive forecasting, meaning when we predict January, then we then use the January prediction together with the historical data to predict February, and so on until we reach the 6 months. So our target is to forecast the full 6 months. As the previous study or journal only used it up to 7 days, so we try to extend this to a longer period. So we start off with an empty code map, basically a product country combination, which is currently empty, and and then we will start filling in the data as we go. We also define a get last price function, which basically, because forecasting month does not have the price information, so we have to take from the previous month, and we assume that the price used is the same as the previous month. So this is also another issue that we face because the Tata dataset does not have a fixed marketing or pricing calendar. In the real world, we would have that. So in this case, we are just assuming the same as the last price. And then also there is some error handling as well in this loop. In the next slide, basically showing that if there's no last price, we will use the global average. Okay, and then yeah, so the temporary bind is basically binding all of the different variables and to help us to predict to help us to do the recursive modeling lah. So all of these features that I talk about, functions that I talk about, live under a for loop. So this for loop will execute for every month, starting from January until month number 6, June. Yeah. So in each, we're still in the for loop. In that for loop, we use the model and we use the predict function to predict the lower value, the median, and the upper value. So this is the model that was trained in the previous session. And then we ensure that the number is also not negative. If it's negative, then we assume 0 because quantity sales cannot be negative. And also we try to make some logical ordering. P upper must be higher than P mid. P lower must be lower than P mid. Yeah, and yeah, basically this whole for loop is the recursive portion where we predict it month by month, and then we send this month data to the next month, and then we fill in the empty product versus country data set that we created initially. And then finally, after we run the for loop, you will go into the final forecast. We'll bind all of the forecast result into final forecast, which will pass this into the Shiny model later for plotting. And then we also calculate the revenue. So this one is actually quite simple. So basically, we calculate the revenue based on the forecasted quantity and times by the last known price. So there is some data cleanup also over here. We remove the revenue is 0, or sometimes the sales is very low, 4 or 5, and the model also predicts a low amount of number in the future months. So we remove all of that to make it 0, and then from there we calculate the revenue. Then we basically combine all of the data and also passed it to the Shiny model dashboard building. So now I pass over to Hani on explaining on the Shiny coding.
Thank you. For the dashboard, the first thing that we need to do is setting up the UI. UI is the interface that we see when we first open the dashboard. Okay, first we use the function fruit page is the container of the whole apps. Okay, the fruit page is the one that make our dashboard will be interactive. After that, we use the theme BS Lib. This one is for a modern, professional, and flat design look on our dashboard. And then we use the title panel. This title panel is for us to make to put the dashboard title. After that, we define the sidebar layout. It divides our screen into a zone where the sidebar panel, and then we have the main panel for the result. Sidebar panel is imagined as the input that the user can click in, change, for example, maybe the stock type. After that, select input, it creates the drop-down menu, and the download button here is for the user to download the report. After that, you see at each of the tab, it contains all the plot for each particular item that we want to show on the dashboard. Our first step is for the forecast, and then we show the revenue. After that, the residual performance. Next. So, this one, like I just now told you about the building dashboard, we will define the tab that we want to show on our dashboard. Okay, after we have defined the UI, we need the server. Okay, the server is important because we can imagine as like we have defined all the engines, so the server is like the startup. Okay, and the reactive here is used because we want to create an interactive dashboard that when the user click on anything on the dashboard that we set, it can automatically update based on the country that the user select. After that, we use the REQ function. That one is because we want, it's like a safety check for us to ensure the code waits until an input is selected before it runs. And then below, down here, after that, we will define all the visualization that we want to show on our dashboard. Okay. The next one, here also we have the download handler. The download handler is for us to download all the file that all the selected filter item that we choose on our server. That's it. Next.
Thank you, Annie. So next session is again from me. Basically, just want to take everyone through the dashboard. So the dashboard has three tabs. The first tab is basically the forecast tab. This is for us to check whether the forecast makes sense or not. And we can also select different countries, and we can also select an alt for the whole data set as an average. The second tab is about revenue. So again, the same, we can select all, and we can also select per country, and to see whether the model is predicting any revenue and in the 2012 forecasted data. And then the third tab is the model diagnostics. So most importantly, the RMSSE, which we use to compare against um, the main journal. And also we have some residual plot functions that which will be explained later. So that's roughly and we can see that some for all the RMSSE is quite high, 2.3. The target is about 0.5 if compared to the journal, and we generally want to be better than one because one is a naive baseline. It's the same as a naive baseline last month guess. So we want to explore a little bit further. Why is our data is a little bit high, the RMSSE? So we look at we call a bit of table to show the RMSSE value, and we also do a Ljung box test to check whether the errors are random or not. And what we found is that from the forecasting data is that in terms of a junk box test, well, first of all, some data set has too little sales value, so there is no prediction and there's not available data over there. Secondly, the junk box test shows that it's all above 0.05, which means that the errors are random, which is good. Okay, we passed the test. However, for the RMSSE, United Kingdom has quite a bad RMSSE value. So you can see this table here that we want to be about 0.5, less than 0.5 or less than 1 in general. If we get 0.501 is what the original paper achieved, which is an 11.5% improvement over the baseline similar to the paper's finding. So you can see that all the other countries is about there, 0.5, 0.6, but for UK, it's very high at 3.1. So if we just look at the forecast data, we can see that, and also the residual plot, we can see that the UK has a very high peak at December. So there is some missing features. So for holiday and promotion, maybe the marketing calendar is different that we don't know, that we can't see from the data set that we have. So for that reason, that's the basically the reason why we believe the RMSSE is quite high for UK. Moving on to the next section is Dalila.
Now the monthly revenue analysis of the project. The visualization attached here are the top 5 countries with high value of total revenue, which also can be seen the value from the table below. We can notice two distinct patterns here. In the United Kingdom and Europe, the blue bars are very jumpy. One month is huge and the next month is a valley. So this is what we call market volatility. In analytics, we see this as seasonal noise likely driven by big holiday sales or one-off promotions. When we compare that to France or Germany, they look much steadier even if their total volume is lower. The black trend lines help see through all those jumps. It is clear the United Kingdom is a lot noisier, but look at the transition into the forecast bars. Our model predicts that after a quiet end to 2011, every country is going to see a major breakout in January 2012. So this visual is basically Tata's early warning system telling to get the inventory ready in Europe before that forecast surge actually hits. To wrap up our top 5 countries analysis, we step back to the quarterly view. It blurs out the small distractions to see if Tata is actually growing or shrinking over the long term. When we compare these countries side by side, the growth story is very consistent. Even though United Kingdom had some rough months in late 2011, the quarterly bars show a very resilient upward climb. We can also see at the recovery in the Netherlands and Germany for early 2012. Those forecast bars suggest a record-breaking start to the year across the board. In business analytics, this high-level view is used to make big decisions like where to hire more staff or open new warehouses. So the conclusion here is simple. While the day-to-day might look disorganized, Tata's internal expansion is on a statistically solid upward path.
Moving on to the next section, residual analysis. So for residual analysis, we will look into three different plots. This is the ACF autocorrelation function plot, the histogram of the residuals, as well as the errors over time plot. So the next slide, please. So for the autocorrelation function, so basically from the previous slide, the SCF plot cut off at 0. So SCF plot shows no spike, which indicates that the model's ability to capture trend and seasonal factor well. In terms of residual analysis, the vertical bars are also within the confidence bounds. This suggests that there is no significant autocorrelation, hence it is a good model. For the the residual distribution, as can be shown in the histogram plot, the residuals are normally distributed and centered at 0. Errors are mostly random around 0, which indicate that there is no systematic structure left, and there is no extreme skew or heavy tails, which suggests that the model captured the main pattern as well. For the errors over time plot, for this plot, residual is basically it's the actual sales minus the predicted sales. So if the value is above 0, so the model is under predicted, which means that actually the actual sales is greater than the predicted sales. And if the value is below 0, so the model basically over predicted, which is actual sales is less than predicted sales. So from the plot itself, in Q1 of 2011, residuals are positive and increases, especially in January 2011. This model tends to underestimate sales in these months, which it predict lesser than what the actual sales are shown. However, residuals stay close to 0 from April to October 2020, positive or negative. At this period, the model had little systematic bias, and that does make that predictions match the actual sales fairly well on average. However, there's a large jump upward in residuals occurs after October 2011, suggests that the model again underpredicted sales substantially. This may likely due to a strong seasonal effect, such as holiday sales surge, that the model did not fully capture, in which case that the actual sales is much higher than the predicted sales due to the year-end sales that the model cannot capture. Hence why there is a high increase in the residuals for during that period. I will pass to the next presenter. Present the next slide.
Yeah, so we will move to the conclusion from the business perspective. So this shows that Light GBM proved to be highly effective baseline for global retail forecasting. So from here, the country level results highlight how it suggests some strategies or suggestions to the stakeholders for different markets. So volatile markets like the UK require promotion and holiday features to improve forecast, in which it allow managers to plan inventory buffers for peak seasons and reduce excess inventory after promotion ends. This also applies to Ireland, which with the volatile market as well. And while stable regions such as Germany benefit from lean inventory planning, while France is identified as a growth market. So where stakeholders may consider for expansion strategy or invest more in marketing and logistics for France. So this shows how forecasting model for like GBM can guide tailored operational decisions across diverse markets. And in this case, we only pick like the top 5 countries. Moving to the next slide, to conclude the general aspect from the general expansion outlook. So our case study validated that like GBM's framework scales effectively to a global data set like Tata's. A unified tree-based model generalized across 38 regions concurrently without region-specific tuning. Then it extends forecast up to 6 months ahead, which is an extension to the previous journal. Okay, then the model achieved an RMSSE less than 1 in the majority of the regions with standout performance in Netherlands and Ireland. So as comparison, the original paper achieved approximately 0.5 RMSSE, and the top performing method in the M5 accuracy competition submitted in 2022 by Yonjun, who also used the Light GBM, achieved a weighted RMSSE of 0.520. So this demonstrates that the simplified tree-based methods is scalable and practical for multinational retailers. Then Mus will present on the limitations part.
Yeah, so basically, what was mentioned in the previous slide, United Kingdom had a very high spike at the end of December, and that is mainly the main reason why the RMSSC for United Kingdom is quite bad. And also, United Kingdom has the highest number of sale in terms of quantity. It also affected the overall all model. If you look at the all inside the uh, dashboard. However, for majority of other countries, the performance is actually very good. So what is missing in our data is the calendar seasonality, which we do not have apart from the price. So if the price change, we have until December 2011 price. But if there's any price promotional strategies that uh, Tata wants to implement, we don't have that data. So there is some limitation in terms of our model. And finally, just to conclude on the recommendation, so basically we can recommend that Light GBM can be used for global retail forecasting across many different regions. So we have 38 region in our study, as well as expanding it to a longer outlook from 7 days initially used in the journal, and now up to 6 months. And we were able to get RMSSC less than 1 for most of our data set. So that is all from our presentation. Thank you very much. How do we stop the recording?
Aku